Let's thank Christian again. Our last speaker for today and also for the whole workshop this year is also our organizers, one of our organizers here, Professor Joe Primack. He's going to tell us about the latest advances of the AGORA project.
First of all, can everybody hear? Yes, you can hear back there? Good. So, the AGORA project was actually started here in Santa Cruz 12 years ago. And this is the meeting for the summary. If you can see the names, the second name after mine is Ji-Hun Kim. And Ji-Hun was at this time a postdoc with Guillermo Madao and with me. And he's been the leader of this project ever since. So we have created an environment where people can collaborate. We've created infrastructure. We've written a series of articles. We've had 12 workshops here at UCSC. We've had 80-some telecons, and we've now published 6 major papers with a bunch of new ones in separation. The key thing about this project has been that we're trying to be very mindful of how to compare simulations by calibrating many things, but leaving some things uncalibrated to correspond to what people actually do with the simulation. We've used and helped to create a number of useful codes and environments: music for initial conditions, Grackle, heating and cooling, YT, visualization and display analysis, Biden, a absorption spectrum generator, and various other ones. A lot of the codes have changed as time has gone on. 12 years is a long time. So the first paper was published led by Ji-Hun Kim in 2014, so 2 years after we started the project. There was a fairly long delay. There's a second paper that came out fairly soon after that, which was not a zoom-in, not a cosmological simulation, but an isolated galaxy that was supposed to represent a Milky Way-like galaxy at, say, redshift 1 with about a 20% gap. Then there was a long delay till the next series of papers, and that's because these are cosmological simulations. It took a long time to get the whole framework set up, but now we've actually made some serious progress. So these are the first 3 papers. These are the new papers that were just published in the last few months. So this is a paper that basically describes the whole process and summarizes many features of the galaxies. And I'm going to show you a few selected examples from these papers. This paper is on the satellite of the Milky Way mass galaxy, as predicted by all these different codes. And this paper is on the circumgalactic media from all these different codes. So the first thing we did was to set up initial conditions and run them sophisticationlessly with pure dark matter simulations, 9 different codes, and a careful, the first approximation, if you look at these, they all look very similar. But when you look very carefully at them, the codes actually differ quite a lot, even though these are pure dark matter codes. The next paper was the isolated disk simulation, and there are 9 codes involved, and there's a big difference in the appearance of the 4 adaptive mesh refinement codes compared to the SPH codes, but surprisingly, the galaxies really look rather similar. The surface density profiles, rotation velocities, velocity dispersion profiles, and they're all pretty consistent with the Koenig-Schmidt relation. How was that possible? Well, it turned out that many of the codes actually had mistakes. Or, if the codes were fine, the initial conditions, for example, the way you set the codes up when you are running an isolated galaxy, had to be fixed. Runtime parameters were found that made the code incompatible initially, and then we figured out how to make them compatible. And there were some errors in the code that became apparent when we did careful comparison. So the next step was to set up what we call the Cosmo run. So these are now fully cosmological zoom-in simulations with the same initial conditions for a Milky Way mass galaxy that had few mergers. It's turning out to have major mergers at around redshift 2 and earlier at around redshift 4. So there was an elaborate procedure to calibrate the simulations. I don't have time to go into the details, but those are all explained in what we call paper 2. Santi Roca-Fabrica was the first author. And so we calibrated cosmology, common heating and cooling, star formation recipe, initial conditions, and we made sure that at redshift 4, the simulations agreed within a factor of 2 or so in the stellar mass generated. We then didn't do any further calibrations, we just let the simulations run. And the next 3 papers are describing what came out. Now, these are the codes that were used. The summary parameters, the global parameters, actually agreed pretty well. This is showing the stellar mass from redshift 6 to redshift 1. Some of the codes have actually gone down to redshift 0. And they agree to within about half a day. And this is the metal generation, the total metal mass as a function of redshift. And they also agree, but that's not surprising because the yields were fixed to be the same in all the codes except one. And that one wasn't very different. So many of the things in the codes, especially these summary properties, were quite similar. We ran all of the codes with pure dark matter and also fiducial versions, including baryons. A number of the codes were rerun several times to fix various errors, to get the initial conditions right, and so forth. Now, this is actually showing you the evolution of all 8 codes. This is dark matter density projection, projected star density, gas density, temperature, metallicity. Some things you can see look pretty similar. Dark matter pretty similar. The gas density somewhat different. Incidentally, there's a filament that all of the codes are on. Okay, so it's not easy to absorb all of this. I'll let it run one more time. So the filament is this way, gas is flowing in this way, and it turns out that it's flowing out largely in this perpendicular direction, by conical outflow. So these are examples of these projected metallicity, hydrogen density, temperature, and radial velocity. Radial velocity, this is at redshift 3, and notice that inflow is coming this way. Oops, sorry. This is turned around. Outflow is going this way. That's radial. That's positive. Red is positive radial velocity, and inflow is coming this way. And the different codes aren't all the same, but there are some sort of obvious similarities. This is the same thing now at redshift 1. At the time the paper was finalized, not all the codes had gotten down below redshift 1. There's a couple more that did. This is just to give you a sense of what's in these papers. This is face-on images of these galaxies. And one of the things that you'll see immediately is that they're pretty different. And also, the Ramses case, Ramses ended at redshift 2, really never made a nice disk. Most of the other ones did make a nice disk. These are the edge-on views of the same galaxies. And again, there are certain similarities, but some of them quite puffy. Ramses here, some of them fairly thin. They're different. The virial mass tracked very similarly, of course. You'd expect that. You'd be surprised it was different. If you know the virial mass and the redshift, you know the radius, so the radii track very carefully. The galaxy stellar mass, remember, it was calibrated at redshift 4, so the total spread is half the dex or so. And it turned out that we just let them run, and they stayed pretty close to the same. This is a sort of typical empirical model. This is from Aldo Puebla et al. And one of the et al. From 2017. Very similar, actually, to Universe Machine. So this is what a typical galaxy of the mass of this one at redshift 0 would look like. And as you see, it's a little bit high. It had a major merger here at redshift 4 and another major merger at redshift 2. That may have affected this. But the thing to notice is that the different galaxies are somewhat different. Now, if you want to see some real differences, the galaxy half-mass radii. And you can sort of see this when I showed you the pictures. But when you actually analyze them, they're really, I think, surprisingly different. More than a full dex different. The inner kiloparsec density varies all over the place, pretty different. The star formation rate, pretty different. I should have said that all the codes were supposed to have exactly the same physics implemented, except for one major difference: feedback. Each code group was told, use the feedback prescription that's most commonly used by people who run that kind of code. So that's what they did. And as you saw, it kept the stellar mass pretty similar. But in many other respects, these are very different simulations, very different galaxies. So all these are remarkably different at many redshifts. Okay, so that was the paper 4 summarizing, and also some of this from paper 6, which is actually on the third black medium. Another thing that we looked at, led by Minyoung Yang, was the satellite, and in particular the question that this paper asked is, do all these codes solve the satellite over-prediction problem? That is, that pure dark matter simulations predict many more satellites than we actually see. So, as I told you, all these codes are run pure dark matter and also with full hydro. If you zoom in, you can see there's a lot fewer with hydro, a lot fewer of these satellites than in pure dark matter. That was true for every one of the codes. So this is number of halos as a function of mass, as a function of radius. And when you turn on hydro, it substantially goes down by about half a dex, sometimes even more than half a dex. And these were all consistent. Since these codes were not all run down to low redshift, it's not completely proper to compare with Andromeda, gas, and the Milky Way. But in general, this is comparing the codes that got down to as low redshift as they could when the paper was finalized. So there are 5 codes below redshift 1. And the basic conclusion was, yes, all of the codes solve the satellite problem. So, as we saw from the beginning, the 8 simulations are similar in some respects, like stellar mass, down to redshift 1. And if you actually look in detail at the feedback that was used, thermal plus kinetic, radiation pressure feedback, thermal in ENSO, etc., the schemes were actually quite different. So it's not surprising that many of the properties were different. And one of the things that turned out to be very different was the certain galactic media. In paper 6, led by Clayton Strawn, who was my graduate student, a number of different things were done. Trident was used to make lots of random sight lines through these galaxies and compare the predictions of a number of different ions with observations. Dividing into some low ions and some high ions, the low ion column densities droplet distance with little code dependence. So they're all basically following a similar pattern. Not much difference between the codes. Not terribly good agreement with observations, especially at the larger distances. The higher ions, oxygen 6 and neon 8, here the codes differ quite a lot, and they all have this similar radial dependence, though. And the codes that have high feedback, so the blue code is ART1, agree pretty well with the observations, and some of the other codes that have much lower feedback agreed much worse with the observations. Now, so that's the papers that have been published now. What I want to talk about now briefly is where we're going from here. So there was a first meeting in person of the AGORA community in Seoul, South Korea, May 7th to 10th. Actually, the first 2 days were a general conference on galaxies with people mostly from South Korea, with a few people coming in from outside, including me and Ken Nagamine. Ken has also been one of the leaders in the project. And so one of the things that we're doing is we're putting a very good sample of all the data that I just showed you in the slides on FlatHub, part of the Flatiron Institute. They're willing to host all of our outputs. We're only putting a limited fraction of the outputs. The paper on that was supposed to be on the archive today. Didn't make it for some reason. I'm sure it'll be out on Monday. And meanwhile, we've started 3 new projects that are moving along rather rapidly. I'm going to show you just some excerpts from those. So one is studying the mergers. I told you there's mergers at redshift 4 and redshift 2, major mergers. Another on how the satellites got quenched, and the third on a more detailed analysis of the morphology of the galaxies that are formed. So these are the 3 that I just described. In addition, there's at least 3, possibly gadget 4, if that's still in the works. Okay, so 4 additional codes that are running the same initial conditions to add to the comparison. And there are several new AGORA projects. Isolated AGN, EKO et al. High redshift first galaxies running a number of different simulations to just compare them at very high redshift 10 and above. A higher resolution version of the Cosmo run. Not sure if we can be able to do that. And a number of other topics have been discussed. So now just to give you a little bit of examples of what's happening. So one project is Kirk Barrow and the students in Nguyen, together with other members of this collaboration, studying the mergers, both the merger at redshift 4 and the merger at redshift around 2. So this is tracking the centers of the 2 galaxies, distance, dropping down, and they were all organized so that this occurs at the same spot, the same time. So it was all arranged. So, and all the codes have a first close passage, a separation, and then another close passage that more or less where the centers merge, except for one. Gizmo merged pretty much in the first close passage. That was odd. What happened during the first close passage, the separation, and the second? So one example of the kind of information that's coming out of this analysis is looking at the first infall, the passage, the fallback, the second pass, and final deposit of data of stars. So this is the new stars created in each of these phases, and it's a function of the circularity parameter, Jz over the J that's required for convergence, for circular support rather. And this is just an example. This was done for all 8 codes, just to show you an example of the difference. So here in the second pass, so the galaxies go past each other, they go apart. In the second pass, there was a bit of additional disk formation, a little bit more positive than negative, JZ over J circular. This was in the ENSO code. The Arepo was completely different. It made a big disk, largely in stars created in the second passage. So to give you a sense of how different codes can be, and of course what's going to be interesting is to understand in some detail why the codes are doing it. That's the point of these papers. So this is a morphology paper, and some of these you saw before, but not in as much detail. This was not shown in detail before. It was the central density. This is now central surface density in the inner kiloparsec. These are the two mergers, around redshift 4 and around redshift 2. And this is the half mass radius and the mass of the disk defined by circularity divided by the total mass. And so you see some of them are making really nice disks and some of them aren't. Okay, the third of these papers in preparation has to do with what's quenching the satellites. And so a number of different things were included: ram pressure stripping, tidal interaction with the galaxy, harassment, which means interaction of the sub-halos of the satellite galaxies with each other, and combinations of these. And this is just analyzing four of the simulations for, I think this was the first of the redshift 4-ish merger. Sorry, forget that. Not a merger. This is four of the simulations looking at the satellite quenching. This will be done for the other simulations. It just hasn't been done as of last I saw reports from this group. So what you're seeing is that overwhelmingly it's ram pressure stripping in these simulations that's causing satellite quenching. So there are actually now 23 models that have been run at least over a significant redshift range. 8 simulations that are fiducial, one by each code. 8 dark matter only simulations, one for each code. 7 additional simulations by different codes that were run basically earlier and then replaced by better simulations. And 10 of these simulations are now down below redshift half. We're now planning these new Cosmo runs that I mentioned earlier, and the outputs have all been uploaded to FlatHub. And as I said, the data release paper was supposed to be in the archive today to coincide with my talk. Oh, it is on the archive? Oh, I looked for it. I didn't. Terrific. Okay. I was going to show. And the last point is, so what's on the archive now is just the integer redshifts, 8, 7, 6, etc., down to redshift 1, but not all the intermediate steps. And there's about 200 or more that were actually stored. They'll all be released, but only after these papers are finished, to give the authors of these papers a chance to do the analysis before it's made generally public. But these papers are moving along fairly fast, so I think all of the data will become available quite soon. This is the paper that Ken says did appear on the archive today. So this describes the data release, and this data is now all public. The paper 4, Santi Rocafabricas paper, says, our collaboration is open to the participation of interested community members in any of the current projects, and also to host new ones, both that make use of the currently available data or that require starting new comparisons. the larger the customer-run set of models becomes, the better we'll be able to study how different seller feedback descriptions affect the properties information of selected systems. So the Agora project welcomes additions to the membership and also to the projects that are done. And this is a particularly opportunity for young researchers to make contributions. And you'll notice that all of the supplementary papers are read by young researchers, all of the follow-on papers. So Kentaro Nagamine circulated this in his talk. I'm just repeating it. And Ken tells me that it looks like the last week in May is favored. The 12th annual workshop for the Agora project will be held online, so rather than having it be a meeting here, since we already had a pre-meeting in Seoul in May, and it's going to be this Thursday of next week, August 8th, from 4 p.m. to 7 p.m. Pacific Daylight Time. And you can just go to the agorasimulations.org/workshop to get more information about that and to join if you'd like. Okay, so one last little advertisement. I was asked by Annual Reviews to write a review article on galaxy formation, and as soon as Annual Reviews makes it public, it will be available. If somebody has an urgent need to see a review article, sooner than that, send me an email. And of course, you don't have time to read this, but I'm going to upload my slides, so you can. It starts out by saying this is a golden age for galaxy formation. Of course, I mean for galaxy formation studies. This is the outline of it's over 300 references. I apologize in advance to everybody whose truly important work wasn't included either because I didn't know about it or I didn't have room. And this is the last sort of figure in the paper. So this is done for annual reviews of nuclear and particle science, not annual reviews of astronomy and astrophysics. And the nuclear and particle science people, of course, include lots of theorists who invent all kinds of weird dark matter or other things to try to explain what they think are the big problems in the field. So one of the things I wanted to do was to summarize what I thought were the really important problems and the not necessarily so important problems. This was inspired by a similar figure just on the dwarf galaxy issues in the Salas Retro Patahi review in Nature Astronomy a couple of years ago. They said planes with satellites is a serious problem, but Laura Salas now thinks that it's not a very serious problem. And Charlotte Welker explained one example of why it's probably not a serious problem. At least in the New Horizons simulations, the planes with satellites are quite abundant. Okay, one last thing. The workshop continues in an informal way starting 11 a.m. next Monday, August 5th. It's going to be we are here now. This is the Core West parking structure. It's going to be in the Interdisciplinary Sciences Building, room 221, right near the courtyard, the Interdisciplinary Sciences Building. How many people are planning to be there on Monday? Okay, keep your hands up because I need to order enough food. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, I count 13. Okay. Okay, would you count? Well, there certainly aren't 25 hands up. 1, 2, 7. Okay. Well, I'll certainly get enough food for at least 20. Are there going to be people coming next week who aren't here this week? Not as far as I know. So, yeah, Andy Berger. Okay. Well, we'll definitely get enough food for Andy. Okay. Thank you, everyone, and I'll be glad to take any questions if there are any. Did I choose? Joe in the back. Oh, sorry, Dave. Then Gilbert Ted.
Should I? Okay. Thanks, Joel. It's been a while since I've kept up with the kind of planning behind Agora, but I wonder if there were any thoughts to, obviously after this new series of cosmological papers, perhaps taking a further step back to some of the hydro stuff and maybe doing a comparison of magnetic fields, MHD effects, which I think is probably a necessary thing in the field. I think there are a lot of discrepancies between codes on how they evolve magnetic fields. Is there any discussion about that among the steering committee?
Not that I'm aware of, but I agree that that's an important thing to look into, and also as soon as you do include magnetic fields, you probably want to include cosmic rays.
Well, I mean, that's a whole other thing, but I mean, magnetic, because, cosmic rays is also dependent on some subgrid stuff. Magnetic fields, it's the same way we compared the hydro solvers, so now you want to compare the MHD solvers.
Right. Definitely a good idea. The problem is always limited person power and also computing power.
Great stuff, Joel. Thanks for this talk and for everything else. Regarding the satellite quenching statistics, how ram pressure stripping seems to dominate in all of the simulations. I'm curious sort of what mode of ram pressure stripping you're talking about. Is this directly removing the gas reservoir from the interstellar medium, or does that include also removing a circumgalactic medium and then the galaxy quenches by starvation? Because I don't see starvation on this list.
The short answer is I don't know the details, but it's going to depend on each code. So one of the things that this paper is going to do is look carefully at how each code is dealing with removing the gas. And evidently strangulation wasn't, well, at least it isn't on this list. I'm not sure if, this is still in an early stage. So it's a good question to what I mean, clearly, once a galaxy becomes a satellite, it generally loses its connection to the cosmic web and ceases to get much gas inflow. One interesting question is, are they finding that the gas is more retained at the center of these satellites than on the outside? One of the things that we've noticed looking at the radial color distribution of satellite galaxies is they tend to have blue centers. This is what you'd expect because galaxies will retain gas better if the each center well at the center and larger radii. But that's an example of an observational test that should be that these simulations should be compared to. Sandy.
So a truly Herculean effort. From the standpoint of outsiders who hear this announcement and think they might want to use these models, it's personally I'm a little worried that they can't do better with radii, because if you can't get radii, what else can you get? So I'm just wondering what you think are the best applications of these models, if you're not part of the group engaged in trying to figure out what they're doing, but rather trying to use them for something.
So Sandy's asking, it's very disappointing that these simulations are getting such different radii and various other properties like central densities, which are so important for galaxy evolution. I agree. Actually, in my view, I discussed that and say that this is a big issue. Well, sorry, but in the text, it's definitely there. As to what this, so what Sandy's asking, if I understand it, is what are these simulations good for if they can't get the things like the radii right? And the answer is to understand in some detail why the simulations are doing what they're doing. So, and therefore, to help us interpret simulations and to make better simulations.
It's super interesting, but we need to move on. Let's thank Joe again for this wonderful talk.